did there. So let's draw a swimming area. Maybe, here we go. And we'll label. So here's our beach. And so we don't need a rope there. We'll call this X. So I'm going to say that X is my width. Gave one to everybody else and not yourself. So my, Jesus, weird. My width is X. And then I need to use rope for each of the vertical sections. So each of these dividers. So if I started out with 240 feet of rope and then I just used 4x feet to make the vertical sections, then I'm going to have 240 minus 4x feet left for the long section. And then we know what function to write in this case because we already did this problem. But in general, like if I had a rectangle, I could write a function for like the perimeter. I could write it for the area. Like there's lots of different things that we can figure out about a rectangle. So the way that we decide that we want to write an area function instead of some other function is that it's what we're asked to maximize. So whatever it is that you're maximizing or minimizing should be the output of your function, of the function that you write. So we have a of x equals length times width, so x times 240 minus 4x. And I'm going to go ahead and distribute here because really the only interesting equation we can solve when the function's in factored form is if we set it to 0, but like we would never set the area equal to 0 because then we wouldn't have anywhere to swim at all, right? Like it would take no rope if the area was 0. So, and then I also rearranged the terms. Like you always want to put these in descending order when we're working with quadratics because things like the vertex formula and the quadratic formula, they use that A, B, and C, right? So it's nice to have it in order. So if I'm looking for the maximum area, what point am I looking for on the graph? What point did we find on that graph when we did this graphically? Yeah, the vertex, right? So that very top point. So every time we see this maximum or minimum, so if we're maximizing or minimizing a quadratic function, that always means to find the vertex. And all the ones we're doing today we're maximizing, but the process for minimizing is exactly the same, right? So depending on the function, it's either going to open up or it's going to open down. So if I happen to give you a function that opens up and ask you for the minimum, then you're finding the vertex exactly the same way as if the function happens to open down and you find the maximum. So we're never going to like give you a function that opens up and ask for the maximum because there like is no maximum, right? So the process is no different to minimize a quadratic than it is to maximize it. The function itself just determines which one the vertex is. So we're going to find the vertex, and then the other question you want to ask yourself when you're maximizing or minimizing is which point or which value in the vertex you want, right? So you can find the vertex, but the answer to a question isn't going to be an ordered pair, right? So in this case, are we asked for the x value or the y value of the vertex? Sorry? Yeah, the y value, right? We're asked for the area, which is the output of our function. So because we're looking for area, we want to find the y value. And realistically, we always have to find the x value first because that's what our vertex formula gives us. But it's nice to get an idea of like what your final goal is because it can be easy in these problems to kind of just start throwing numbers around and get lost in like what exactly it is that you're finding when you start plugging things in and stuff like that. So our vertex formula is x equals negative b over 2a. So x equals negative 240 over 2 times negative 4, which is 30. Oh, one thing I did want to show you guys. We just found the x-coordinate of the vertex, right? So but our final answer is the y-coordinate because we're asked for the maximum area. So what this is this is the width that will maximize area. And I can't emphasize enough like how helpful it is to just label everything. Like I said, like there's a lot that goes on in these, and you can like start spitting out numbers all over the place. Like, you know, we have more than one formula that solves more than one equation that gives us more than one value. So you want to really be aware of like what points you're actually finding when you find something. So every time I solve an equation, every time like I get a number in a problem, like an application problem, I always stop and ask myself, like, what did I just find in terms of the problem? Like, before I go and do anything with it. Because, like, you can kind of start going on autopilot, and then all of a sudden you just have, like, 20 numbers, and you don't really know what any of them are. So we just found the width that will maximize area. We want to find the maximum area, so we're going to plug that width into our function.
Can you plug it into either function, or does it have to be that second one?
Oh, you could. They're the same, so you can plug it into either one. And I'm pretty sure that's 3,600. And so the maximum area.
Isn't it negative?
The whole thing is 3,600, like positive 3,600. Like when you do negative 4 times 30 squared, you get negative 3,600, but 240 times 30 is positive 7,200. Minus 3,600 is positive 3,600. Yeah? Okay. The maximum area is 3,600. What are my units?
Square feet.
Square feet, yeah. Good. When I printed this out this morning, I got so mad at myself because on your homework it's in yards, and like 80% of you wrote feet instead of yards, and like now I'm just reinforcing that mistake because I made it feet this time, like when I typed it like this time. It really irritates me. But nonetheless, any questions on what we did, why we did it, how we did it? So far so good? Okay, so let's do this next one. Okay, so a couple things about this. That came from my screenshot. We'll make it go away. Bye-bye. Okay. Oh, I should get it away from the watermark. There we go. So this problem is really similar to problems we've done before, right? But we're going to approach it in a little bit different of a way. So the first thing I want to point out is that none of this will be given on the test. On the test or your homework. So we put those on the notes so we can like help guide you through how to set it up. But like when you actually do the problem on your own, like we expect you to be able to set it up. So the problem will look like this, and then it'll like ask these questions. Would be like the whole problem without all that stuff in the middle. again, no, these are like the problems we've been doing like all semester with this like demand relationship where like price goes up and quantity goes down. But the way we're going to approach it here is like, remember like was it just last week when we last did this? When we did this, we had to write a linear equation for like the quantity. So like X was the price. We had to like get 2 points by making a table, then use those 2 points to write a linear equation, and then use that linear equation to write a revenue function. So there was like quite a few steps to that. None of which were like totally trivial. So instead, we're going to make X the price reduction. So how much we lowered the price. And by doing that, we can come up with an expression for the price and the quantity a little bit more easily. And we can forego that step of having to write that linear equation for the quantity that we had to do last week. So the way that we're going to write those two expressions for my price and my quantity. So, well, I guess first we should talk about the fact that the reason I want an expression for my price and my quantity is I'm writing a revenue function, right? And revenue is price times quantity. So I have to express my price and my quantity first in order to write a revenue function. I find the easiest way to do it is with like a little table. So like we have a price and a quantity. Are the things we're dealing with. Quantity. And we're given like an initial price and quantity. And then they're both either going up or down by some amount, so some change. And then what we end up with is our new price or quantity. That's going to be the expression that we use to write our revenue function. So what's our initial price? $100. And what is the quantity that corresponds to that price? 400. Good. So that's the way you always want to think through it, is like there can be a lot of different numbers in the problem depending on what information it decides to give you. And so when you look at your initial price, you want to ask yourself what quantity corresponds to that, and that way you'll pick the right number out. It's the amount that you can sell at a price of 100. And then is the price going up or down?
Down.
It's going down, right? We know that because it says that X is the price reduction, so this is a minus. And then that means that the quantity is going up, which they tell us, but also, it's always a negative relationship. So if price goes up, quantity demanded goes down, and vice versa, which means one of those will always be a plus and one will be a minus. You just have to figure out which is which. And then how much is my price changing by in general? So that dollar, like, okay, so if the price changed by $1, then that would mean that we were going to price our coats at $99. Problem done, right? Like, there's no relationship there, right? So that dollar isn't like a set amount that we're lowering the price by. It's more of like a rate. It's saying that every time you lower the price by $1, our quantity demanded goes up by 8, but it's not saying we're going to lower it by exactly $1. It's just telling us how much the quantity changes every time we do it by $1, right? So what are we calling the price reduction here? So look for the words price reduction.
X.
Yes, X is the price reduction in dollars, right? So price reduction is the number of dollars that I lowered the price by. And so that's X. You always want a variable in here because otherwise we don't have a function, right? In order to talk about a relationship between price and quantity, like we have to have a variable in there somewhere. Otherwise, nothing's changing. And so you're just saying like, oh, I'm going to sell it for $99 and I'll be able to sell 408 of them, right? There's no relationship of changing values there. So then if I lower my price by X dollars, how much does my quantity increase by? So we could put y there, you're right. But then,
Like 8x?
yes. Let me talk about y real quick, and then we'll put 8x there. So if we put y there, then we would have to go back to what we did last week and write an equation for the quantity in terms of the price, right? Because our revenue function can only have one variable in it. And so if we put a y here, then we have to go back and be like, okay, what does y equal in terms of x? So we can plug that in. And so the reason we're choosing to set it up this way is to eliminate the need to do that. And so we're just going to use 8x. Right? So the quantity, the change in quantity is the change per dollar times the number of dollars that we lowered the price. So this is the change in quantity per dollar, and this is the number of dollars we're lowering the price. Right? So if I lowered the price $3, then I would get an increase of 24 in quantity. So then reading across horizontally, that tells me my new price and my new quantity. So my new price is 100 minus x, and my new quantity is 400 plus 8x. And so that's what's going to go right here. So 100 minus x, 400 plus 8x. And then how do I find my revenue function?
That's price times quantity.
Yeah, revenue is price times quantity. And that will be on your test, like in the box on top. So when you get to a problem that involves revenue, you can turn to the front and make sure you get the equation right. So price times quantity. So R of x equals our new price times our new quantity. And then we'll go ahead and distribute. So we get R of x equals 40,000 plus 800x minus 400x minus 8x squared. Bless you. So I'm going to put that in descending order and combine like terms. That gives me my revenue function. R of x equals negative 8x squared plus 400x plus 40,000. I'm running out of room. So when you're doing your setup, like you could just do that table and like you don't have to necessarily list all of this if you just do the table and then you use these. Like that's labeling it enough, I think, that you can go back and find what you need. So now let's determine the price reduction that results in a maximum monthly revenue. What do I need to find? The vertex. Do I want the x coordinate or the y coordinate? So the price reduction is, yeah, that's x, right? So this is the x value. I want a maximum, so of the vertex. So we have x equals negative 400 over 2 times negative 8. I think it's 25. So I just found the price reduction that will maximize revenue. And so now, so all of that is what you have to do just to set the problem up so that you can answer these questions down here. So what price should I sell the coats for? $75, yeah. So this whole setup that we did gives us everything we need to answer the questions. You just have to go back. Yes?
Why does it equal 25? X equals negative 400 over 2 times quantity.
Isn't 400 divided by 16 25?
Oh, right. Okay, never mind.
Oh, okay. I've been saying it's 25 for the past like 3 hours. I hope it's 25. Yeah. Because 400 divided by 2 is 200 divided by 8. Okay, yes, okay. So if we want our price, we just go back up to here and say, oh yeah, the price is 100 minus my x value. So price is 100 minus 25. And then how would I find the number of coats?
Multiply 25 by 8.
Plus
And yeah, we just use this expression, right? So one thing, like, I bug you guys about setting things up and like labeling. And one of the reasons is that once you set everything up, you can just use everything you've already, like you give yourself everything you need. So don't try to like go back and like restart the problem every time you're answering a new question. Like use what you've given yourself already. And that way you don't have to like figure everything out over and over and over again. So our quantity is 400 plus 8 times 25, which is 600. And then what would the easiest way to find the revenue be?
600 times 75.
Yeah, in this case, we found the price and we found the quantity, and we know revenue is price times quantity. So the simplest thing to do is just multiply 75 by 600. And I think that's 45,000.
Mm-hmm.
If we hadn't found the price and the quantity, then we would plug 25 into our revenue function, right? So you can also find your revenue function or your revenue just by plugging your X value into your revenue function. But in this case, that's kind of overkill, right? Like we might as well just multiply them because we found them. Yeah? These are fun, right? Let's throw some more stuff up in the air. Can you guys change this? Oops. Change this to a 1. Every semester I say I'm going to change that, and I do. It like 2 is all like already on the way down after 2 seconds, so it's kind of weird to ask how much like it gains after 2 seconds if it goes up and then starts coming down. Like we can do it, but it's kind of a weird answer. So we're going to find a lot of things about the path of this here stone. So I'm going to draw a picture of the graph. Because one of the challenging parts about these problems is you have to figure out like what you're trying to find and like how to find it, right? Like we have all these formulas. We have the quadratic formula, we have the vertex formula, we have all these different forms of the functions. And it can be easy to get mixed up or to go on autopilot and like just start plugging stuff in. But we want to keep in mind like where exactly we are on the graph, because that's going to tell us like how to approach it, right? If we're finding x-intercepts, if we're finding y-intercepts, if we're finding the vertex. So if I want to know how much height the stone has gained in the first 1 second, well, first, can I just say it gained 60 feet? Is that a true statement? Why not? I mean, if it's going 60 feet per second. Yeah, because that's only the initial velocity, right? Like, gravity's acting on it. So as soon as you shoot it up in the air, the velocity starts decreasing. Like, it goes slower and slower, like, the longer it's in the air, and then starts going faster and faster as it falls, right? Because gravity is acting on it from the instant that you shoot it out. So we can't just be like, oh, it's going 60 feet per second, so in 1 second it goes 60 feet. Because it only goes 60 feet for, like, not even, like it's instantaneous. So it's, like, as soon as you shoot it out, it slows down. So that's why we use our function. So what should I do first, do you think? Yeah, let's plug in 1 because that's going to tell me its height after a second, right? So here's like my 1 second. I'm going to find h of 1, which is negative 16 times 1 squared plus 60 times 1 plus 30. So h of 1 equals 74. So is that how much height we gained after 1 second? No, right? That's like that's how far I am off the ground after 1 second. But I didn't start on the ground, right? So this distance right here between where I started and where I ended up after a second, this is the height gained. In the first second. So h of 1 is the height I am at after a second. And then if I take my initial height away from that, then we get, let's see, 74 minus 30. So that tells me that we gained 44 feet. So now we want to find the time at which the stone reaches its maximum height. So what point am I looking for? The vertex, right? Because I see that maximum. Am I looking for the x-coordinate or the y-coordinate of the vertex?
Why?
Sure. So am I looking for a time or a height? A time, and that's my input, right? So you want to ask yourself if you're looking for an input or an output. The x-coordinate's always the input, the y-coordinate's always the output. So we are determining a time, so that's the x value. We are maximizing, so that's the vertex. So we have x equals negative 60 over 2 times negative 16. And that gives me 1.875 seconds. And then what am I finding in part C? The y-coordinate of the vertex, right? So what is the height? So this is the y-coordinate. I always say coordinate and then write value because I don't like spelling coordinate. Y value of the vertex. So we're just going to evaluate our function for 1.875 seconds. Plus 60. Which gives me what? Good. So the max height is 86.25 seconds. What now? Feet. Feet. Yeah. Thank you. Talk about going on autopilot. There we go. Okay, so now I want to know how long the stone is in the air before it hits the ground. Am I looking for an input or an output? Input, and how am I going to find it?
Output 0.
Yeah, the output is 0, right? I'm looking for this point right here when we hit the ground. That's an x-intercept. So, hits ground. Which means that h of t is equal to 0. So negative 16t squared plus 60t plus 30 equals 0. How should we solve that?
Factor?
Yeah, we can factor. I'm going to make sure that we can factor by doing b squared minus 4ac. So what do you get when you find the discriminant? Yeah, the discriminant is 5,520. And then if you take the square root of that, do you get a whole number?
No.
No, so we can't factor. Right? So we could only factor if that's a perfect square. So since we can't factor, what should we do? Quadratic formula, and we already have the discriminant, so we're like halfway there. So t equals negative b plus or minus the square root of the discriminant over 2 times a. And I'm gonna change this again. You guys got that all done? Because this is another one where plugging it into your calculator is kind of simple to mess up. So again, you want to use that fraction button if you have it. If you don't have a fraction button, then put the entire numerator in parentheses and the entire denominator in parentheses. But if you have your fraction button, you can just hit it and you do negative 60 plus. There's no plus or minus in your calculator. You have to do like one at a time, right? So then the square root of 5,520 and then 2 times negative 16. Hit enter, and that's not right. Oh. That should be a 1. Okay, there we go. So we get negative 0.45. And then to do the other one, like you don't have to type it all in again. If you hit the up button twice to get there, and then hit enter, and then you can just arrow over to the plus button and make it a minus, and then just hit enter again. And that way you don't have to like risk typing it in wrong by having to do it twice. So 4.2. So how long was the ball in the air? 4.2 seconds, right? Because it can't be negative. Okay, last problem. You're still writing? You good? Okay. So I trust you guys know how to plug numbers into functions at this point, so I'm just going to tell you what these are. M of 60 equals 35. What does that tell me? What does that mean?
When you're going 60 miles an hour, you get a 35 miles per gallon.
Yes. So x is my speed, so that's my input. And m of x is my gas mileage, so that's my output. So at 60 miles per hour, the car gets 35 miles per gallon. And then m of 75 minus m of 60 is, so we plug 75 in, we already plugged 60 in, and then we subtract them, and it gives you negative 18.75. What does that mean?
That the difference between the mileage is negative 18.
Yeah, so when you drive 75 miles per hour, you get 18.75 miles per gallon less than if you drive 60 miles per hour, right? So when we write a sentence, there's a lot of ways you could say that, but you want to make sure to indicate the direction of the change with a word, not with a negative sign, right? Because nobody talks that way. Like, nobody says, like, I made negative $30 this week. They say I, like, spent $30 this week. So at 75 miles per hour, the gas mileage is 18.75 miles per gallon less than at 60 miles per hour. That's how my mom always used to try to get me to, like, slow down. It was like trying to make it like a financial thing. She's like, you'll save so much money if you drive 55 instead of 70. Like, really, will I save that much money? In this car, you probably would, because that's a big difference, but I don't think the difference is quite that much in real life. Okay, so let's find what speed will maximize gas mileage. What am I looking for? The vertex, right? Am I looking for the y-coordinate or the x-coordinate? So I'm looking for speed, right? So these are tricky because the thing we're maximizing is always the y-coordinate. But when we find the point where that y-coordinate is maximized, that point has an x value and a y value, right? So we can be looking for where the y-coordinate is biggest, but reporting it in terms of the x value. So, like, if we're saying at what speed is the gas mileage maximized, we're looking for where the gas mileage is the largest, but we're looking for what speed you're driving to make that happen, not for what the gas mileage itself is. So the speed is an input, so that means it's the x value. And the fact that I'm maximizing tells me to find the vertex. So x equals, oh, where am I? Negative 2.8 over 2 times negative 0.03 gives me what? 46 point, is it 7?
Yeah, it's
Yeah.
yeah.
Miles per hour. So gas mileage is maximized at a speed of 46.7 miles per hour. These are fun, right? Come on, they're a little fun. Like a little bit. They're at least a little satisfying when you get done, right?